Hey guys, today we're going to talk about acid-base titrations. So we talked about titrations a little bit in Unit 4, but the general idea is that you have your two reactants, one in the flask that you don't know the concentration of, we call that the analyte, and one in the burette that we do know the concentration of, and that's the titrant. Occasionally we'll flip those around, but it winds up being the same procedure where you slowly add some of the titrant into the analyte until you reach equivalence point, or as close to equivalence point as you can get. And sometimes we'll use a color changing indicator to tell us when the end point is met, which is hopefully again close to the equivalence point. And then you just need to see, like, okay, so if your burette started here, how much did I use to get to that end point? And so that is the volume of the titrant, and that's going to be important for your calculations when you're trying to figure out the concentration of the analyte. Typically, burettes are labeled upside down. So this is your burette. I'm just drawing it a little bigger. So you'll have 0 milliliters at the top, and if it's a 50 milliliter burette, you'll have the 50 milliliters at the bottom. And so that way, if you filled it all the way up to the top, that means you haven't added anything yet to your analyte. And then as you slowly add a little bit at a time to your analyte, this level will go down, and whatever the reading is, that's how much is gone, how much you used for your reaction. So, I don't know, 10 milliliters. That means you used 10 milliliters for your reaction, you have 40 left in the burette. Just be careful with your sig figs and make sure that you're paying attention if it's reading upside down. They like to ask questions about burettes in terms of significant digits on the AP exam because it always throws people off when it's upside down. Let me use some more realistic numbers. So if I have like 5 milliliters, right, and then 6 milliliters, this is not to scale, but then I have my liquid volume is there, you would say that that reading is like 5.5. I'm sorry, 5.05, because you know it's between 5.0 and 5.1, and you estimate it's about halfway through. So this one would have 3 significant figures. So that's kind of your general procedure for titrations. Now, one of the most important purposes of a titration is to figure out the concentration of an unknown solution, which we call our analyte. You're looking for the equivalence point. And that's where the moles of the analyte is equal to the moles of the titrant stoichiometrically. Okay. So if you have reactant A plus B yields C plus D. If it's a 1-to-1 ratio, that's really easy. The moles are equal at equivalence point. But if it's not a 1-to-1 ratio, then you need to be a little bit more careful. Okay, so let's say it takes 2 of A to react with every 1 of B. What you would do if this is your analyte and this is your titrant, you would take the volume that it took from your burette at equivalence point and convert that to liters and times the molarity of the titrant. So all of this is for the titrant. That will give you the moles of the titrant. And then you would do a mole ratio, moles of the titrant. Well, I'll just use B, moles of B. There's 1 B for every 2 A in the reaction. So you'll have twice as many moles of A at equivalence point. So when I put equals here, it's not really an equals, it's when they balance out stoichiometrically. Okay. Once you have moles of A, then you can divide by your original liters, moles of A, moles over liters will give you the molarity of your unknown solution. I will say that 1-to-1 ratios are a little bit more common, especially when we're doing acid and base titrations, but that doesn't mean that they won't give you a 2-to-1 or a 3-to-1 or whatever. So just pay attention to that. Find moles, do a mole ratio, then go back to molarity when you're looking at equivalence point. Another note that is important that a lot of people forget is that it does not matter if it's strong or weak. So when you're figuring out the concentration of the unknown solution, it doesn't matter if it's strong or weak, you're just looking at the moles. What does matter when it's a strong or weak acid or base is the pH throughout the titration. That's going to be different. It's just how you calculate your concentration is the same. So these are what we would call titration curves. This is where we're tracking the pH on the y-axis versus the volume, usually in milliliters, but it's the volume of the titrant. Volume of the titrant. So as you add a little bit more from your burette, you're tracking the pH over the entire titration. This first graph is a titration of a strong acid titrated with a strong base. That means a strong acid is your analyte. We know that it's your analyte because you're starting at a really low pH. So that's your strong acid to start out with. That's in your flask. And then the strong base is what you're adding in slowly because the pH is getting higher, and that's in your burette. Now, when you have a strong acid and strong base titration, what's really nice at equivalence point is that it will always wind up at a pH of 7. And you'll notice the distinct shape for a strong acid, strong base titration. Now, the volume of the titrant, you're going to find by looking for the most vertical section of your titration curve and just halfway through that most vertical section. And when you find that most vertical section, that volume of the titrant, that's going to be what you use to calculate concentration. So you'll change that to liters, multiply by the molarity to give you moles, do your mole ratio, and then convert that back to molarity of your analyte. Now for the weak acid with a strong base titration, it has a different shape. You can see automatically it's increasing, but it flattens out for a period before it starts to increase again. The equivalence point is still halfway through the most vertical section. Okay. The pH for a weak acid with a strong base titration will be above 7. Depends on the specific weak acid, but it'll be somewhere above 7. And you'll still trace down to find your volume of the titrant, and you're going to use that volume just like you would with a strong acid, strong base titration, and find your moles, do mole ratio, convert back to molarity. There's a cool thing with weak acids, you can actually get a little bit more information out of it at what we call half equivalence point. So sometimes I'll write a V1 half. It's half of the volume that it takes to get to equivalence point. At half equivalence point, the pH of the solution is equal to the pKa of the substance, which is super helpful because then if you have the pKa, you can find the Ka. You just do 10 to the negative pKa. I'll give you the pKa. We'll give you the Ka for that weak acid. So if you're not sure what acid it is, you just know it's weak, you can do a titration to find the pKa, which is kind of neat. So just be careful there. We also, a couple more bits of information, we would also call this the buffer region because it kind of flattens out in pH, so the pH is staying relatively constant there. And we're going to treat it like a buffer when we're doing calculations for that section. Now let's take a look at titration curves when we're starting with a base. So we still have pH versus the volume of the titrant. pH versus the volume of the titrant. This one is going to be a strong base titrated with a strong acid. The strong base is the analyte. We know because it's starting at a high pH, so that must be what's in your flask. And then you're slowly adding in the acid, so it's getting to be a lower pH, and so that one must be in your burette. Now, just like with the strong acid, strong base titration, it will have a pH of 7 when it's at equivalence point, which is super helpful. And you can find the volume at that point to use for your concentration calculations. For the weak base with a strong acid titration curve, you're still going to have a lot of the same things. The halfway through the most vertical point is the equivalence point. The pH will be somewhere below 7 at equivalence point. You can still find the volume at equivalence point to use to calculate your concentrations. You can also find the pH at that half equivalence point. So this still holds true. pH is equal to the pKa, but it's the pKa of the conjugate acid. So you could take 14 minus the pKa, that will give you the pKb for that weak base. And you can use that to find the Kb of that weak base if you need to. So that gives you some useful information there. And of course, notice the difference in shape between strong base with strong acid titrations and then weak base with strong acid titrations. We always use a known solution that is a strong acid or a strong base. We never use a known solution that's weak. We never titrate two weak things together. It just makes it too complicated. So you might be asked about some polyprotic acids. Polyprotic just means multiple protons or multiple hydrogens. So if you have something like H2SO4, that would be a diprotic acid, and you would have a titration curve something like this. Now, but this one's a strong acid, so that's probably not the best example. I'm trying to think of a better one that's we could do H2CO3, diprotic, because it's then it's going to have two equivalence points. So the first equivalence point is here, the second equivalence point is there, because of those two acidic hydrogens or two protons. So that's a diprotic acid. You could also have a triprotic acid. This could be maybe H3PO4, or it could be like citric acids, triprotic. This one's going to have three equivalence points. We usually call them, Ka1, Ka2, Ka3. They're also going to have multiple pKas because of that, and multiple like half equivalence points, if that makes sense. So you'll have you'll be able to find the pKa here and here, pKa here and here. Now it's not really appropriate that I labeled it Ka. It's like equivalence point 1, equivalence point 2, equivalence point 3, based off of those three different points in the titration. Okay, so let's connect these titration curves back to what we were talking about in section 4 with calculations for acid and base reactions. At the very beginning, and this is a weak acid with a strong base titration. The very beginning, all you have in there is that weak acid. You haven't started the reaction yet. So you're going to perform these calculations just like you would from section 8.3, where you're using the Ka and the ice chart. You're figuring out the concentrations at equilibrium to find the pH of the solution. In terms of particles at the solution, your weak acid HA, we'll do that, is going to dissociate just a little bit into hydrogen ions and your conjugate base, but a very, very small amount. You have significantly more of the undissociated acid in the solution at that time. Now, at equivalence point, we know that all of the acid has reacted with the base. So, present in the solution at that time is just your conjugate base and water. So you'll need to use the Kb of that conjugate base to solve for the pH at equilibrium. It will be above 7, but you'll need to follow the instructions, use a BCA chart, and then Kb of the weak acid to find the pH at that point. Half equivalence point, we know that the pH is equal to the pKa, and we know that our acid concentration is equal to the base concentration. It's halfway to equivalence point, so half of the moles of the acid have reacted and turned into the conjugate base. So at half equivalence point, those are equal to each other. In between, in this region here, we know that the pH is lower, so my weak acid is going to have a higher concentration than the conjugate base. And then in this section, we're past that half equivalence point, but before the equivalence point, and the pH is increasing, so we know that there is more of the conjugate base than the weak acid. And then, of course, past equivalence point, you have that excess hydroxide ions in there because you're keep adding the strong base. You also have the conjugate base and the water. But the conjugate base is not going to affect the pH very much at all because of that excess hydroxide overpowering it. Let's go through the same thing for this weak base strong acid titration. At the very beginning, before you add any strong acid, you have only that weak base, B. And remember, the B is going to react with water. The base is going to react with water to form HB plus and OH negative. Okay, but at the very beginning, since it's just the base and water, only a very, very, very little bit of it will actually form your conjugate acid. So it will be significantly more concentrated in terms of the base. Now at equivalence point, all of that base has reacted, so we're left with just the conjugate acid and water present there. So at that point, at equivalence point, we know that the pH will be below 7 because of the conjugate acid. You can use the Ka of that conjugate acid to figure out the pH exactly at equilibrium. At half equivalence point, we know that the pH is equal to the pKa. We also know that the concentration of base is equal to the concentration of the conjugate acid. So that's at half equivalence point because half of the base is reacted to form conjugate acid. So in this section, at between the start and the half equivalence point, our pH is higher, so I know that I have more base than conjugate acid. And in this section in here, the pH is decreasing. I know I have more of the conjugate acid than the weak base. And then, of course, past equivalence point, I mostly have just that excess hydrogen ions from the strong acid. I'll also have the conjugate acid and water, but the conjugate acid has very little effect on the pH when compared with the excess hydrogen ions that are present. So make sure you're able to tell what's present at each point during titration and what's present in like the higher quantities versus lower quantities. Okay, so for this example, we are given a strong acid, strong base titration curve. We need to estimate the equivalence point and then determine the concentration of HCl. So the equivalence point of a strong acid, strong base titration is at pH of 7, which is right here at 25 milliliters of sodium hydroxide. And in liters, that's 0.025 liters. They tell us the molarity is 0.121 for the sodium hydroxide. And when you multiply that, you get 0.00303 moles of NaOH. Now at equivalence point, the moles are equal, so we have that same number of moles of the strong acid. And we started with 20 milliliters or 0.020 liters of HCl. So when you divide that, you get 0.151 molar for the HCl. Okay, so the graph below shows the titration of oxalic acid with sodium hydroxide. Label the equivalence point, estimate the pH, and estimate the pKa. So we know that this is a weak acid. It's not one of our strong acids, and you can kind of tell from the shape we've got a little bit of a buffer region here. It's not perfect, but it's close. Label the equivalence point. So the equivalence point is halfway through that most vertical section. So that is our equivalence point. It's at a volume of about 30 milliliters and a pH of maybe 8.5. Okay. So estimate the pH equivalence point is about 8.5. Estimate the pKa. Okay, so pKa, you're going to use the half equivalence point. So if it took 30 milliliters to get to equivalence point, it needs to take 15 milliliters to get to half equivalence point. So right here, so it's maybe about 2.5, 3. Because it does say estimate, you won't be docked by if you're off a little bit. They always give a range of values for estimation. But I would say maybe 2.5 or 3 for that pKa.